What specific problem does this paper address regarding the training of large language models, LLMs, and how does it seek to fill existing gaps in scaling law research?
This paper addresses the challenge of efficiently estimating the performance of large language models, LLMs, during training, particularly for practitioners with limited computational resources. It highlights the gap in existing scaling law research, which typically relies on exhaustive training of closely related models, by proposing a practical guide for selecting small-scale models that can provide reliable predictions about larger models' behavior. The authors emphasize the importance of balancing the number of models, their sizes, and the dataset used to maximize prediction reliability while minimizing costs. By conducting a large-scale meta-analysis of diverse model data, the paper aims to generalize scaling laws across different architectures and datasets, thus providing a more comprehensive understanding of how to effectively utilize small models for estimating the performance of larger ones. Ultimately, it seeks to improve the decision-making process for practitioners by offering insights into when and how to use small models to inform the training of larger LLMs.
How does the proposed method of estimating scaling laws work? Illustrate the methodology step by step, including any novel components introduced in the process.
The proposed method for estimating scaling laws involves several key steps. First, a diverse dataset of models is collected, which includes various model families and their performance metrics, allowing for a comprehensive meta-analysis of scaling behavior across different architectures and datasets. Page 2. Next, the methodology defines a scaling law as a function that predicts a target model's loss based on the performance of smaller, cheaper models that share the same pre-training procedure but differ in size and training tokens. Page 3. The estimation process utilizes intermediate training checkpoints rather than only final model performance, which significantly improves the fit of the scaling law. Page 5. Additionally, the method emphasizes the importance of training multiple smaller models with varying sizes and hyperparameters to reduce variance and enhance prediction reliability. Page 9. Finally, the scaling law parameters are estimated using curve fitting techniques, specifically the curve_fit function from scikit-learn, ensuring that the model captures the relationship between model size, training tokens, and performance accurately. Page 4.
Can you provide a simple example to demonstrate how a scaling law is estimated using smaller models? Walk through the main steps of the algorithm using this example.
To estimate a scaling law using smaller models, we can follow a structured approach as outlined in the paper. First, we collect a set of smaller models that differ only in size and the number of training tokens, forming a scaled model family. For instance, if we have 3 models with sizes of 1B, 2B, and 3B parameters, we would train these models on a common dataset. Next, we would evaluate their performance by measuring their loss on held-out data, which allows us to gather empirical negative log likelihood values. Using these values, we apply a curve-fitting algorithm, such as the curve_fit function in scikit-learn, to estimate the parameters of the scaling law that predicts the loss of a target model based on the performance of the smaller models. Finally, we validate the estimated scaling law by comparing its predictions against the actual loss of the target model, ensuring that the model's performance can be reliably extrapolated from the smaller models.
What are the key theoretical and practical benefits of using the proposed method for predicting the performance of large language models compared to existing methods?
The proposed method for predicting the performance of large language models, LLMs, offers several key theoretical and practical benefits over existing methods. Firstly, it allows practitioners to estimate a target model's performance using a diverse set of smaller models, which can significantly reduce computational costs and time associated with full-scale training runs. The method emphasizes the importance of using intermediate training checkpoints, which enhances the accuracy of scaling law predictions, as opposed to relying solely on fully trained models. Additionally, the approach highlights the trade-offs between the number of models, their sizes, and the dataset used, enabling more informed decisions about resource allocation. Finally, the findings suggest that even a single training run from a new model family can yield accurate scaling law predictions, thus streamlining the process of model evaluation and selection.
How are the proposed scaling laws validated or tested in the paper? Discuss the experimental design and the metrics used to evaluate the effectiveness of the method.
The proposed scaling laws in the paper are validated through a systematic experimental design that involves estimating scaling law parameters from a diverse set of model families and evaluating their predictive accuracy against empirical losses from target models. Specifically, the authors identify the maximal parameter family for each model family and use the remaining models to estimate the scaling law parameters, employing the curve_fit function from scikit-learn for this estimation. To assess the effectiveness of the scaling laws, they calculate the mean absolute relative error, R, between the predicted loss from the scaling law and the actual empirical loss observed at various checkpoints near the end of training. The paper emphasizes the importance of including intermediate checkpoints in the training process, as relying solely on final performance often yields poorer predictions. Additionally, the authors explore the impact of model size and the number of models on prediction accuracy, demonstrating that increasing the number of models generally improves the reliability of the scaling law estimates.
What specific results were reported in the paper regarding the performance improvement of scaling laws, and how do these results compare with previous findings in the field?
The paper reports that scaling laws can predict model performance with a mean absolute relative error, R, of less than 10% when using a diverse set of models, which is a significant improvement over previous findings that often relied on single model families or minimal variations. Specifically, it was found that using intermediate checkpoints during training enhances the accuracy of scaling law predictions, contrasting with earlier assumptions that only final training results were informative. The authors also highlight that the variance in loss due to random parameter initializations can reach up to 4%, and meaningful changes in model performance have been observed to be at least 4% in past studies, suggesting that the scaling laws developed in this paper can reliably capture these nuances. Additionally, the paper emphasizes that different model families exhibit varying scaling law behaviors, indicating that a more nuanced understanding of scaling laws is necessary compared to previous, more generalized approaches. Overall, the results suggest that the proposed methods for estimating scaling laws provide a more reliable framework for predicting large model performance than traditional methods in the field.
What are the identified limitations or drawbacks of the proposed scaling law estimation method, and how might these affect the practical applicability of the findings?
The proposed scaling law estimation method has several identified limitations that could impact its practical applicability. Firstly, the use of the absolute relative error, R, as the primary evaluation metric does not differentiate between overestimation and underestimation of model performance, which may lead to overly conservative error estimates when selecting between candidate models. Additionally, the challenge of aggregating information across different model families is significant, as many published families evaluate models at incomparable scales and ranges, complicating the ability to produce a comprehensive and informative overview of scaling behavior. Furthermore, the findings suggest that the scaling laws may exhibit fewer degrees of freedom than previously assumed, indicating potential misspecification in the functional form used for estimation. Lastly, the reliance on intermediate checkpoints rather than final performance may introduce noise, particularly if the early training phases are not adequately accounted for, which could skew predictions. These limitations highlight the need for careful consideration when applying the scaling law findings to real-world model training scenarios.
What future work do the authors suggest to further enhance the understanding and application of scaling laws in model training?
The authors suggest several avenues for future work to enhance the understanding and application of scaling laws in model training. They propose exploring different functional forms for scaling laws that could better account for the relationships between parameters, as their findings indicate that scaling laws may exhibit fewer degrees of freedom than previously assumed. Additionally, they highlight the need to consider the learning rate schedule in future models, as their current experiments did not adequately address its impact on training dynamics. The authors also mention the potential for improving efficiency in predicting model performance by better adjusting scaling laws during training. Lastly, they indicate that future research could focus on optimizing the selection of model sizes and the number of models to train, which could lead to more effective scaling law estimations.